Howdy. In this video, we're going to consider collisions between gas molecules and a surface. The simplest case to imagine or to envision is just collisions with a molecule striking an actual physical surface. It might be the wall of a container, it might be, say, a crystal of metal that is somehow suspended in a gas volume, something like that. We could, as it turns out, use the same equations and think about the flux of molecules through a plane, just any imaginary plane in a vessel of gas, and that would work just the same. But for now, we're going to picture an actual surface because it's easier to think about. So over here, I've drawn a little cartoon which represents the situation. So the cross-hatched area there represents my solid surface. I've got a surface just sitting like this. I've got some gas molecules coming down toward it from above. Okay, so the blue circles there represent my gas molecules. They are all having components of their velocity coming towards the surface, so they're candidates to collide with it. Okay. If I do this, what I'm going to do is take that drawing and imagine looking at it kind of sideways. So down here, imagine that we've now rotated things so that my surface is coming in and out of the plane of the screen. All right, that's represented by this here is my surface now, and I've taken on it an area A that I've highlighted, that circle. Okay, so A represents the area of that circle. Think of that as the target. We're going to calculate how many molecules actually strike that particular piece of surface in a given time window, okay? To begin with, let's imagine I just have one molecule that I'm isolating and looking at, okay? My molecule starts out here. That's my molecule sitting there. That molecule will reach my surface in a time delta t as long as it's moving towards the surface with a speed vx. It'll reach it as long as its starting position is within this distance down here of the surface, okay? So here's my surface. If I trace out a distance equal to vx times delta t, remember vx is a speed, so it's got units of distance over time, right? Multiply that by delta t, that's a time, so now I've got distance. So vx delta t is a distance. If I start off any place in this range, then by the time delta t has elapsed, I will have reached the surface and struck it, okay? Now, I really want to have more than one molecule, okay? So to do that, I'm going to imagine that I construct this cylinder represented by the area of the circle on this end. So the circle down there represents one of the circular end caps of my cylinder. The dashed lines here represent the walls of the cylinder coming away from my surface. And then I've drawn a second circle out here, which represents the other end of the cylinder. Okay, so the area of both ends is just equal to A, and then the height of my cylinder is equal to that distance on bottom, Vx delta t. Down to the bottom of the screen, I can say the number of collisions that should take place in time window delta t is going to be a function of n over v, which we might refer to as the number density of the gas, okay? It's not the traditional mass density, it's number of molecules per unit volume, okay? So if I take that number density and multiply it by the volume of my cylinder, we said all the molecules moving with Vx that start inside that cylinder will reach the surface, okay? So if I take that volume and multiply it by the number density, I'll get how many molecules are in there. That's how many molecules can hit the surface in that length of time, delta t. All right, so remember that equation on the bottom, which is n over v times the area of the target on the surface times Vx and delta t. What we're going to do next is correct for the fact that we kind of implied all the molecules have the same speed in that last argument. That's not true. We know that molecules have a range of speeds, and we know that those speeds are given by the equation for the Maxwell-Boltzmann distribution function. Right? So now, if I compare this equation up here with the one on the previous slide, what I've done is all this stuff has taken the place of what used to just be a Vx. Now, there's still a Vx in there, right? But what this has done is it's multiplied Vx at any given speed, it multiplies it by this f of Vx. That's the fraction of all the molecules that have that speed. And then it does that for every possible speed. That's what the integral does, because I'm integrating over dvx, right? So the total range of speeds is from 0, that's the slowest possible speed, up through infinity. If I can do that integral, then that will give me the expression that I need to get the flux of molecules to the surface, okay? So we're going to define this flux, call it F here. The flux is going to be number of collisions per unit area per unit time. So starting from my number of collisions equation on top, if I divide that by A, that's the area, and delta T, that's the time, then I'm going to get this flux in collisions per area per time. I have an A delta T up here. I'm dividing by A delta T down there. So those are going to cancel, right? So that term disappears. In the bottom line, this N over V comes directly from this one, okay? What I've done now is inside that integral, I've taken the F of V and I've replaced it with the equation, the functional form for that Boltzmann distribution function, which is just all of this stuff here, right? That's all F of V. I still got Vx and I still got the dVx there. In terms of the integral, this piece in parentheses and the square root, that's a constant in terms of the integral because it doesn't have any Vx terms in it. So that says I could also pull that term outside of the integral to put it out there with the N over V. On the next slide, we're going to do that, and then we're going to deal with trying to evaluate the integral. Okay, so this just says I pulled that through the integral. So all this stuff here is independent of Vx, so it doesn't get changed when I integrate it. Turns out there's a standard form that says that that integral there is equal to 1 over 2a, where a is just whatever is multiplying the x squared piece in the exponent. That form matches the equation that we've got, right? Because here I've got a Vx squared in there. Vx is my variable I'm integrating over. So think of that as being in the role of x. Here is a Vx, so that's the x dx piece. So that's this and that. My exponential piece then is the e to the minus ax squared. That means to translate that, I say that a is equal to this quantity here, m over 2kt, because that's the stuff that's multiplying v squared in the exponent, okay? If I do that, when I do my integral, what I'm going to get for my flux is this. The n over v and this parentheses term, those are the ones that used to be outside of the integral. This 1/2 here comes from that 2 in the bottom right there. And this last term there, that's my 1 over a from the result from that standard form integral, okay? So that gives me my flux equation now as a closed form, as an equation that I can just calculate. If I know the mass of the gas and I know T, then I'm good here. To clean that up some, we can swap out N over V in front of that with a P over KT. That just amounts to using the ideal gas law, okay? If I do that, I get this somewhat gawky looking form here. I say gawky looking because that one's got KTs all over the place. It's got a couple of different M terms in it. So there's a lot of cleaning up we could do on that. And if we do all that cleaning up, we arrive at the last form over here, which is relatively simple, right? It says that this flux of gas depends on the pressure. That makes sense. If I raise the pressure, I've got more gas in there. They should hit the surface more often. It depends on the mass of the molecules, and it depends on the temperature. Those things are influencing the speed, so they're influencing how fast the molecules are going. The faster they're going, the more likely they are to be striking the surface, okay? So that equation gives me the random flux of gas molecules per unit area. That's going to have units of molecules or collisions, say, per unit area per unit time. So if I was in SI units, this would be in 1 over meters squared and seconds, say. So it's the number of things striking a particular area in a particular time. That equation can actually be recast in this form, and that one does pop up some. If you read further along in chapter 6, you'll see that form invoked. I'm still, to be honest, figuring out whether we're going to take up all those topics from the latter part of chapter 6 or skip to selections from 7 for the last little bit of our class time. But if we do use this, we'll see that form down there. In here, the V bar that's there, that's just the mean speed or the average speed. If you think back for the equation for those which we derived earlier, it's got pi and k and m and t in it, and so that's going to take out some of the constants that are in the top form, okay? The n over v there, that could also, we can think of that as coming from a p over kt, so that would also let us do some algebra to get from here down to there if we wanted to. And you can certainly work through that on your own if you care to try and prove to yourself that that works. All right, to finish out this video, we're going to do an example in which I'm going to calculate an estimate for the time that it might take to contaminate a clean surface. okay? It turns out there's a lot of applications that require really clean surfaces. A great example of that is all sorts of things that get done in the semiconductor business, where they grow really pure surfaces and then deposit on them small trace amounts of various substances, things like that. To do that, you have to start off with a really clean surface, and you have to know it's not getting covered up by stuff that you don't want there, okay? To do this calculation, we're going to need to know a few facts. One is sort of a rule of thumb from surface chemists, and I actually used to be a surface chemist when I used to do science experiments. And one of the things I remember is that we always used to say, well, there's about 10 to the 15th atoms per centimeter squared in an exposed surface. So that just says if you take, say, a crystal of any old metal, slice through it, if you could count up the number of exposed atoms in a 1 square centimeter area, it's going to be on the order of 10 to the 15th. It's not an exact number. Exact number would depend on what particular material you were talking about, what plane you cut in the crystal, things like that. But it's close enough for this estimate, okay? Next up, we're going to assume that every time a gas molecule strikes the surface, it sticks there. It stays attached to the surface. It doesn't ever bounce off, okay? And lastly, we're going to say that one gas molecule comes in and covers up one of those surface atoms. So if I want to cover up all my surface atoms, which is what I'm calling to totally contaminate the surface, I'm going to have to stick 10 to the 15th gas molecules per square centimeter to my surface. I'm going to calculate how long it takes to do that at 10 to the minus 6 torr pressure, and I'm going to use 300 Kelvin for the temperature, which it looks like I didn't actually put on the slide here, but let's just make a note. We're going to do this at 300 Kelvin because that's just a convenient temperature for us, okay? The other thing I'm going to do is I'm starting to calculate is I'm going to just declare the gas. I'm going to use nitrogen for my gas because it turns out in a recent example, we did some things with nitrogen, so I have some parameters for it handy. So that's our problem right there. I'm doing 300 Kelvin. I'm using nitrogen for the gas. The first thing up is I'm going to do some unit juggling to get things in shape to put in the equation. So let's start off with the pressure. We have 10 to the minus 6 torr. Okay, that 10 to the minus 6 torr, I want to convert that to pascals because that's the SI unit of pressure, and I want to do everything in SI units like I usually do. So I'm going to say, I'm going to do this conversion by using two conversion factors that I happen to know. One is that 760 torr are 1 atmosphere. So that tells me this pressure is fairly low. It's on the order of 10 to the minus 9 torr, right? If I round that 760 to 1,000. So it's a pretty low pressure. It's not hard to pump something down to that pressure, but it takes a little bit of work. And then I'm going to say, that I also happen to know that 1 atmosphere is equal to 1.013 times 10 to the 5th pascals. Because that's just a thing that everybody knows, right? No, it's really not, but it's okay. If you were doing this, you might very well have to look up a conversion factor. You might, in fact, look one up that went straight from torr to pascal, and that would be just fine. I happen to know those two, so I use those. If I divide that out and all, I get 1.33 times 10 to the minus 4 pascals. Okay, I'm also going to make a note here that the mass of a nitrogen molecule in kilograms is equal to 4.65 times 10 to the minus 26 kilograms. That one, we could start with 28 AMU for our molecule, right? And then convert the AMU to kilograms. If you didn't happen to have a conversion factor handy for that, you could invoke the fact that a mole of AMUs is equal to 1 gram and get there from there. Just a little fun fact on the side. All right, now it's time for the actual calculation. So my pressure is now 1.33 times 10 to the minus 4. I'm going to put in newtons per square meter for my pascals, right? Because that's what a pascal is. Then I'm going to do some brackets because everything down here is in a square root. 2 pi, m is 4.65 times 10 to the minus 26, and that's in kilograms. I have Boltzmann's constant, which we know and love. That's 1.38 times 10 to the minus 23 joules per Kelvin. My temperature is 300 Kelvin. All that is inside the square root, okay? If I parse the units for that, it's very easy to see the kelvins go away, right? To resolve the rest of them, you kind of have to take care of the fact that you can express your newtons and your joules in base units and then cancel some stuff. I will leave it for you to convince yourselves, if you'd like, that the units do work out. And when I multiply this through, I get 3.82 times 10 to the 18th. And that's got units of 1 over meters squared and 1 over seconds, okay? My first reaction is that sounds like a big number, but then I look at it and I say, well, it's for a square meter, right? That's a very large area. A 1 meter square is going to be a big target, so a lot of molecules will hit that even in this 1 second interval. Because I'm calculating for covering up my surface, and I know I said I had 10 to the 15th atoms per centimeter squared, I'm actually going to convert this to be per centimeter squared instead of per meter squared. So I'm going to take this, I'm going to multiply it by a piece that says 1 meter squared. I'm putting the meter squared on the top because over here in my units, the meter squared is really on the bottom. 1 meter squared is 10 to the 4th centimeters squared. So that's going to knock me down a bit because if I'm hitting the smaller target, I'm going to hit it less often. Times 10 to the 14th. Now I'm in 1 over centimeters squared and 1 over seconds, okay? So what I asked myself to find was a time. What I have right now is essentially a flux or a collision rate per unit area. What I want to know is I want to know how long does it take for 10 to the 15th collisions to take place on a 1 square centimeter area. So if I think about that, the way I'm going to do this is, you can tell that I've got 1 over seconds here. So I'm going to want to divide by that to get seconds, right? That's kind of a clue. I'm going to say I want to have 10 to the 15th collisions per square centimeter. And the rate at which my collisions are occurring is that 3.82 times 10 to the 14th happen per square centimeter per second. If I divide those two things, the centimeters will take one another out, and I'm left with seconds on the top. And when I do that and do the arithmetic, my notes claim I get about 2.6 seconds as the time that it would take to completely cover up my 1 square centimeter of surface, to cover up all of those 10 to the 15th exposed surface atoms. That's a pretty short time, right? So that points to the need that if we really wanted to have a clean surface for long enough to do a meaningful experiment of any sort or to grow a material, we're probably going to need a much lower pressure than that 10 to the minus 6 torr. And in fact, when I said I used to do surface chemistry experiments, we used to routinely work at pressures more like 10 to the minus 10 torr than 10 to the minus 6 torr. If I took the pressure down to 10 to the minus 10, my equation up there says P is just in the top, right? So that would increase the time by a factor of 10,000. So that would give me, 20,000 seconds. That's on the order of a quarter of a day. So that would be about 6 hours. So I could do a reasonable experiment, even if it was going to take an hour, and say I didn't have a whole lot of just random contamination of my surface in that time window. And that's exactly why people that do surface chemistry spend a lot of time and money getting to be able to pump things down to those very, very low pressures. As you could imagine, it's not simple, it's not trivial to pump something down to 10 to the minus 10 torr. It's doable. There's lots of vacuum systems on campus that can do that, but it's not a totally trivial process. Mostly it just means you have to spend a lot of money on pumping equipment. All right, that gives us an equation that lets us calculate the flux of molecules to a surface or through a surface, which is an equation that can be used in a lot of different contexts. Thanks.